Hi, and welcome back to the channel. In this video I'm going to be using the 4-to-1 transformer that I built in the last video, and I'm going to be using this little device to build a long wire antenna. This is going to be an off-center fed dipole. It's going to be about 66 feet of wire up in the air. I've been wanting to do this project for a long time. This should be a really fun project, so follow along and enjoy. In my last video, I was winding the 4-to-1 balun for my off-center fed dipole. And here's what I ended up with. So my 4-to-1 balun's inside this waterproof box. And then I've got coax attached to that. And down here we have a common mode choke. That's just 12 turns on a 240-43 toroid. The toroid is painted. And it's just a piece of 1x1 tubing that's long enough to attach to the tower. And we'll attach it to the tower with these U-bolts. So you can see I have some 14 gauge wire here. I think this is 14, it might actually be 12. But anyway, I've got this wire looped around this support, which isn't electrically connected to anything inside that box. It's just a support. And then there's a piece of heat shrink to mechanically hold it in place. And then we've got this loop that goes in the box, and inside the box it attaches to the balun. Same thing on this side. So this holds or takes all the strain and tension. And then this is at a downward angle so water doesn't run into the box. I also drilled this hole at an angle up through the box like this. So water shouldn't get into the box unless we have a wind and rain. But I think I'll probably put a dab of silicone on there to maybe even try and prevent that from happening. And then of course the other end is just going to be tensioned. So I've made these out of an old cutting board. This works. This is kind of a neat little secret for machinable plastic. Usually cutting boards are made out of Delrin, and it's an extremely machinable material. So what I'll do is I'll put this through like so, and I'll put another piece of heat shrink right there. And then of course the other end of it will be rope, and that'll tension it at an angle, downward angle, because it is a inverted V dipole. It's an inverted, technically it's an inverted V off-center fed dipole. So I've got two of these, one for each side. Here's my spool of coax. And then one end's going to anchor to my roof with just a loop, kind of like an eyelet. Something like this, except more with a wood screw on the end of it instead of this bolt. And then the other end of it is going to be anchored between two trees. I'm going to sling a rope between two trees and then attach the other end to a rope that will go up to the other side of that dipole to tension it. And then I can move that rope up and down so that my angles are the same left to right. And then we'll check it for SWR. And I'm sure I'm not going to hit this. I'll be very surprised if I hit the right resonant frequency first time around. I might have to shorten it, I might have to lengthen it, but what I can do is if it's way off on all the bands I want to run with, I can strip a little bit of this, and then I can just attach a couple short pieces of wire, like maybe 4 to 6 inches, and then check SWR again. If that doesn't change anything, or if it changes it in the wrong direction, I can move over to the other side and attach a 4 to 6 inch piece of wire and check it again on all bands. And if that makes it worse, then we can start trimming. And since this is an off-center dipole, this leg will be longer than this leg. So if I take 1 inch off of this side, I would need to take 2 inches off of this side. And just trim it until the SWR starts to come in line, and then if it's still high across the bands, or let's say I'm high on 40, low on 20, then I'll have to maybe shorten one leg and lengthen the other, or vice versa. and just play with it until I get my lengths correct. And then once I figure out what the ideal length is for the two bands that I want to run, which is 20 and 40, with maybe 10 as a kicker, then I can take this wire off and I can measure it. I have more wire, and I can set the new piece of wire to the exact length that I've determined this should be after trial and experimentation, and go ahead and put it up in the air. And who knows, I might hit it first time around. I could get lucky, and as far as I'm concerned, if it's 1.5 or lower, actually if it's 2.0 or lower, I'd probably just run it, but I prefer 1.5 or lower at the most, maybe 1.7 or lower, and hopefully even lower than that. So we'll know shortly. I plan to put it up this weekend, so I will I'll run some SWR checks on it and see where we're at. Here's our finished product. This is mounted, coax run through the wall, and I just went down and I anchored it to the porch roof over here, right there. And then on the other side, I've got it attached some rope, and it's attached to the carport. Right there. Now I can start tuning, and that's what I'm going to be doing right now. And we've got the coax run through the wall. Time to put the PL259 on the end here. And then we're going to cross our fingers and check it out and see where we're at. So, might get lucky. You just never know. I kind of guesstimated the length, and it's entirely possible that I nailed it. Probably not. I'm probably going to have to tune in several directions to get it where I want it. These antennas are a pain. They're not simple antennas to tune because you're not just tuning for one band. You're tuning for multiple bands. And the nature of an off-center fed antenna is that you're trying to pick a point where the resistance at the feed point of more than one band lines up. And that usually takes some trial and error. So I'm expecting that of the two bands that I want this thing to be resonant on, 20 meters and 40 meters, I'm kind of figuring that it might be close on one, but not both. And we'll probably have to do some trimming. Now, if it's right on the money on one of my bands, but way off on the other, that means that I didn't calculate my lengths correctly. And when I start fine-tuning it, I'm going to have to add or subtract wire from one leg. And that's going to be trial and error. I'll just have to take a 4-inch piece of wire and clamp it to one end and see if it's close. And if it's relatively close, then go ahead and recut and set it up for both bands that way. So if it's equally bad on two bands, and with the nano VNA I'll be able to tell kind of which way I have to go. But and then again, it's not something that you can deduce by looking at SWR, because you don't know if your resistance is on a downward leg or downward resistance curve or an upward resistance curve. And there's really no way to know that. So, once again, experimentation is what it will take. So I'll just have to add length to one leg, do another sweep, add length to the other leg, do another sweep, and just kind of play around with it until I get it where I want it. And once I start to do that, I'll be able to see a pattern emerge. And hopefully the pattern will tell me how much I need to add and on which leg I need to add it to. Now, since this antenna is using a transformer, you can't check your PL259 with an ohm meter because it's going to measure short just by the nature of the transformer. So we're just going to have to plug it in and do an SWR sweep, and that's how we're going to tell if I soldered this thing on there correctly. Something else to be aware of with antennas that are resonant on more than one band is spectral purity of your transmitter. So on something like a ground plane or a beam that's cut for a single band, you don't have to worry too much about that because your antenna is only resonant on one band. And once you get away from the center frequency, or wherever that antenna is resonant on that band, there's an automatic signal reduction. However, this antenna is going to be resonant on several frequencies. And if the radio that you're transmitting on isn't very clean, it's possible that those signals will get radiated along with the primary signal, which would be bad. And one of the reasons I got this nano VNA is because I want to experiment with low-pass filters, and that's one way around that. Okay, we'll calibrate. Put our 50 ohm calibrated resistance in there. And we're calibrated. Now we'll pick our frequencies. Now this time we have to cover a broader range. So we want an antenna that's resonant on the SSB calling frequency on 40, 20, and if we're lucky, maybe we'll get 10 too. So I'm going to start off this frequency sweep at 6 megahertz, and I'm going to end it at 28,500 megahertz. Now I'm going to get rid of my traces. I only need the yellow trace, which is SWR. now is when we cross our fingers. Let's put it on SWR. And there you have it. So let's see where we got. So that is probably our 10 megahertz resonance. It's showing 1.1 at 28.5. That's not bad. There's 28.05 and it's still 1.3. Now we'll come over to the next resonance. Oops. And what did I do? Format SWR. There we go. So right there, and that's not going to work. That's 17 megahertz. So let me check this one. Let's see this one. This one's 13. So we need to change our lengths a little bit. It's resonant on 10, but it's not resonant on not resonant on 20 or 40. Back to the drawing board. After much trial, test, and length changes, I've come to a determination. And that determination is going to have me go in a radical direction. But let me outline where I'm at and why I'm going to do some drastic alteration of this antenna. So I put tuning stubs on both legs, the short leg and the long leg, and I just monitor the SWR as I changed the lengths. And what I found out was that I never got 40 meters where it needed to be. I got it down to about 2.2, 2.3, and I really want to see it 1.7 or less. Okay, there we go. So that was yesterday. And today I'm just going to double check, make sure those numbers did not change. This antenna started out at 45 feet on the long leg and 23 feet on the short leg. Right now it's 21 feet on the short leg and 45 feet. So I've cut 2 feet off of the short leg. Let's see, 6 and 30. And here's where we are. So 10 meters is essentially unusable. By cutting 2 feet off the short leg, it moved the resonance higher in frequency. It's now 29,760, and it's about 1.4. And there's this little double hump here. This one's 26,160, and it's about 1.9. And then before, at 17 megahertz, we had this little dip. That's still there, but now it's 2.7. And here's our 20 meter dip, 13,920. So it's calling, let's see. There's the calling frequency. It's 2.4, so not good. And we'll get down to, there we go. So 6,960, 7.2, we're 2.2 and 2.5 to 1. Still too high. And the wind's blowing today, so you'll see those numbers move around a little bit. So, moving the lengths around, what I was able to do was make everything worse. So you can see here, I'm going to ignore this 2.1 right here. I don't believe that's accurate because if you look down here, it's 2.4, and then 2.5, 2.3, and that's essentially where I was. Now, that's 40 meters. Here's 20 meters. So 20 meters started out at 1.5 with a 23-foot short leg and a 45-foot long leg. And then I started trimming it. So I cut half a foot at a time, and the 40 meter number really didn't change. It stayed high. And my 20 meter number started going up. So here you can see it's still 1.5, but here it's 1.6. When I got it down to 21.5 feet, here it's 1.7. And then over here, I raised the short leg to take some angle out of it, so the number didn't change. And then I cut another half a foot off of it, and I went up to 1.8. And all through that, my 40 meter SWR never really changed. And here's what's going on. So I kind of used the classic 33% short leg and 66% long leg rule. And when you do that, essentially what you're doing is when you're looking at the antenna, so a 40 meter half wavelength looks something like this as far as the antenna is looking at it. And normally we would feed it in a regular dipole. Normally we'd feed it right there in the center. And right there in the center we would have about 50 ohms. So we'd run it with just a 1-to-1 Vallon and hook the coax, or you could even hook the coax straight to the two equal length legs and be done with it. So this is for 40 meters. So when you're running an offset or off center fed antenna, what you're going to do is come over instead of being at the 50% mark, I'm going to run over here to the 30% mark, or 33%. And from there, when you feed it, you're looking at probably 300 ohms. Still 40 meters. So I've slowly been shortening the short leg, and what's been happening is I've been moving that feed point down that curve, but it didn't change enough to make the band resonant enough to get the SWR below 2.2, 2.3 to 1. So my 20 meter SWR started getting worse, and here's the reason that happened. When you're looking at 20 meters, at the center 50% point, instead of being full current, it's going to be zero current. And what you're going to have is this. Like that. So by feeding it at the 30% or 33% mark here on 20 meters, in the beginning it was pretty good. It was 1.5 to 1, 1.4 to 1, 1.5 to 1. But as I moved the feed point, what I started doing was moving up that slope. So current increases, impedance decreases, and my SWR starts to go out of whack. So here's my drastic solution. What I'm going to do is I'm going to switch from the 33%, 66% feed point to a 20%, 80% feed point. So I'm going to move my feed point down the slope. And hopefully I can catch the downslope of the 20 meter resonance and catch it good there, and also find a point on 40 meters where the current has dropped enough and the resistance has increased enough that my SWR on 40 will improve. So I'm trying to find a happy medium between 20 and 40. And let me bring my traces back here. Okay. So that's the Smith chart for this antenna. And you can see we're centered on the 40 meter resonant point, and we're only reading 23 ohms. So impedance is too low. We need to increase it. Now if I come over here to 40, you can see we're up a little bit. Now we're at 31. And if I come all the way up to 10 meters, which is 20 something megahertz, you can see we can get that down to 1.4 to 1 and 35 ohms. So if we can get the impedance up, the SWR will come down. And hopefully, by offsetting my feed point over here, we'll get there. So essentially what's going to happen is, instead of having a 21-foot, 45-foot split, we're going to have a 13-foot, 53-foot split. And then I'll reevaluate it and see where we're at. Okay, rather than bore you with all that tedious adjusting, I'll just show you the final numbers that I've come up with. So my final dimensions are 11.5 feet on the short leg and 53.5 feet on the long leg. And that had the desired effect. So I'm going to check all the bands that this thing is resonant on now. And there's quite a few. So we'll start at 6 meters. So we're setting at 51 megahertz right now, 51,570. And at 51,570, we have 1.24 to 1. And then, of course, if I take it down to the usable part of the band, here's 5,100. We're 2.3 to 1. Yeah, 2.36. Okay, so that's a bonus band. And then we have this odd hump here at 37 megahertz, which we'll ignore because that's useless for us. And here's 10. So it's more than 10 actually, it's 30 megahertz. 010, 1.14. And let's see, the usable part of 10, we're about 2.8 to 1. .81. So 10 is still usable, especially with a tuner. All right. Here's 21 megahertz. And we're 1.76 to 1. And of course, that's 15 meters. And it's usable. And now, in fact, let me go ahead and change our display, because truly these are the two bands that I am most concerned with. So here is 20 meters, and right in the middle of the 20 meter band at 14,370, or 1.58 to 1. Which is outstanding. And now we're going to go down to 40 meters. And at 6.9, 6.998 megahertz, we are 1.27 to 1. Now I'm a general, so I can only talk on 7.175 and above. So let me go there. Get a little more accurate here. So there's 7.128 megahertz. And at 7.128, we're still 1.54 to 1. And there you have it. So I can talk 40 meters and I can talk 20 meters without a tuner. Easily. So I consider this to be a total success. And it was just by moving the feed point that I was able to get these numbers. So you might ask, why does moving the feed point work? Or a better question would be, why did I have to move the feed point in the first place? If the 33% rule or 66% rule is supposed to work on an off-center fed dipole, why didn't it work in this instance? And the answer to that question is every antenna installation is different. In my case, I'm not very high off the ground, and I've got a huge carport made of metal that's close to the long leg of the antenna, and I think those two things conspired to lower the feed point impedance enough that I had to move the feed point. So we can do some quick math and find out exactly what our ratio is. So 11.5 plus 53.5 equals, so we're 65 feet total length, and 11.5 divided by 65 equals, we're at 17.6, call it 17.7%. So the short leg is 17.7%. And our long leg is 82.3%. Those are our numbers, 17.7%, 82.3%. And I have seen before, I've seen 18% used as a number and 82% used. So in a low-to-the-ground installation, that's probably good advice. But in my case, very happy with the outcome of this. I just have to finalize. I have to go out there and either pull off my concoction of jumper wires that I've strung together on the long leg and replace it, or more than likely I'll just solder a piece in and go ahead and insulate it and tie it off. But there you have it. Very successful off-center fed antenna that's usable on at least 3 bands that I can see, so I'm very happy. Thanks for watching.